right. Okay. All right. Can people see this again? Let's see. Present now. Window. All right. Are we back on? Can people see now?
Yes. Yeah, I can see two of you.
Okay. Very good. All right. You should be able to see two, and you should see the outline of the slides on one. Great.
Yeah, the slides are up. Yeah, outline. Yeah.
Okay, so first we're going to review the what we've been talking about a little bit, just on the turbulence, just to touch on the turbulence and instability stuff again. Then we're going to jump into Thorpe's book. And so this week we're looking at the first 3 chapters of Thorpe, and then we're going to switch over to Wingard's book and look a little bit at the atmospheric boundary layer by contrast. There's a lot of overlap between the 2 books, so you should be able to quickly skim the kind of parts that are covering the same material as we've seen before, or at least I hope so. So remember that one of the key aspects of turbulence that we want to think about is the idea that there's a spectral progression. So in the traditional Kolmogorov sense, there's injection of energy at large scales that flows down across the inertial range with a local transfer assumption that every wave number is communicating to its neighbors, its larger and smaller neighbors, flowing energy, which is at a rate epsilon, across those wave numbers to a dissipation range. And if you do the dimensional analysis of that, which we did in class 2 weeks ago, you find that the energy power spectrum and the energy per unit wave number as a function of wave number is proportional to that rate of energy transfer to the 2/3 power times the wave number to the minus 5/3 power. So that's the 3D result. But we talked through the fact that in 2-dimensional turbulence, there are actually 2 conserved invariants, energy and entropy, and we quickly saw how the energy was transferred to larger scales and entropy was transferred to smaller scales, and that there are 2 different cascades, an inverse energy cascade and a direct entropy cascade. And so if you inject energy and entropy at some intermediate wave number called the stirring wave number, then you would get dissipation of entropy at small scales and transfer of energy at large scales. And the key point here is that this means that you get different scalings and different steepnesses of the energy power spectrum, and also different estimates of the different viscous scales that are dissipating energy or entropy in the 3D and 2D range. So this is really building on the theory that was originated by Kolmogorov and Kraichnan later. One piece that we quickly went over, but I think we should pick up a little, is whether 2D turbulence is a good proxy for stratified flow in the first place. That's not so obvious. We've talked about not only 2D turbulence, but also QG turbulence and QG instabilities. We saw that a lot of things are similar between them, like the Rayleigh criterion has an extension in the Charney-Stern-Pedlosky necessary conditions for stability. And so we have those 2 ways of thinking. But if you just think a little bit about what happens at the ocean surface, there's going to be maybe a mixed layer, this piece that we've talked about that's turbulent, and then it's going to be hooked into a thermocline below where the flow will be trapped between different density layers. And so the QG theory might explain the stuff down in the thermocline, but in the mixed layer where where the isopycnals are more vertical, maybe we don't know quite what's happening there. And then there's also this Ekman layer, which we keep dodging, but we're going to talk about in a minute. So it's not so clear that 2D turbulence is an obvious, that there would be anything in this system that looks like 2D turbulence. So we're going to come back to that theme after we talk a little bit more about the 3D turbulence that lives in the mixed layer, and particularly in the Ekman layer, and how to think about that today. And remember, the key idea was in the shallow water equations or in the QG equations was the idea of potential vorticity, which is expressing the rotation, particularly on a planetary frame, of a rotating fluid together with the stretching and squeezing terms. It turns out that there is actually a QG turbulence that looks an awful lot like 2D turbulence with an inverse energy cascade and a direct entropy cascade, and things are a lot more complicated in a way that we don't really need to go into in detail right now, but we'll revisit this topic when we get to thinking about the submesoscale and how that works. All right. So that's our catching ourselves up with what we wanted to think about for the 2D and QG theory. Are there any questions on that before we move on to the starting to talk about what Thorpe discusses?
Forcing scale is the same as stirring scale?
Yes, we're going to get to a distinction between stirring and mixing and diffusion in a minute. One of the things, if you remember our video of the rotating fluid versus the 3D fluid, the 3D turbulence fluid, and 2D and QG, there's this phenomenology where things get very long and stretched out before they break up into smaller scale turbulence or are diffused. And so in the earth science literature, people like to talk about the stirring scale as being the scale at which those phenomena are getting stretched out first. And then after they're long and wispy, then there's kind of a mixing and diffusion scale in the short direction, but actually their energy is cascading to larger scales. So broadly, yes, the forcing and the stirring scale are kind of the same thing, but we're going to start learning to use stirring in a special way to imply the straining of the flow field, stretching out uniform blobs into long, thin blobs. Okay, so let's move on. So one of the most noticeable things about the ocean surface, if you're sitting at the beach or on a boat, are waves. We also will think about the aspects of waves. Waves will make our oceanic boundary layer a little different from our atmospheric boundary layer. We're going to talk about Stokes drift and those aspects later after we get into that, some of the scaling ideas. But I just, Thorpe starts with waves because waves are a way to think about the kinds of motion that happen to the ocean surface. So here there are big rolling waves, and then there are also white caps, and then there are these streak lines of foam. All of those are different characteristics of instabilities that happen at the ocean surface. And as you can imagine, many of them have a turbulent characteristic at small scales. So there's some kind of complicated cascade from this scale of waves or this scale of streaks down to turbulence. Here's a little movie which shows what the ocean surface looks like away from shore. So this is there's a lot of different wavelengths of waves. There's not a whole lot of white caps, not a whole lot of breaking waves, except for where there's this boat plowing through. You might wonder where this is taken. I believe this is a video from something called FLIP, which is a floating wave and turbulence observing platform that they have at the Scripps Institution of Oceanography. So I think this is a boat coming over in the direction of FLIP, which is kind of a cool thing to see. Okay, so the original description of a boundary layer in the ocean was figured out by Ekman, and the mathematical description. And the goal really was to explain an observation. So Ekman was a young scientist who worked together with Nansen. Nansen had gone up and frozen his ship, the Fram, into the Arctic ice pack for a year, trying to get to the North Pole on this kind of crazy adventure. but also took a lot of scientific observations while he was up there. So for the one of the things that they noticed was that the icebergs did not float, and the sea ice didn't float in the direction of the wind. They floated to the right of the wind. And so that was a very peculiar thing that nobody had a good sense of. And so Ekman made a theory, but it's actually kind of a nice introduction to what a boundary layer theory might look like in geophysical flows. So let's talk our way through this, and this is what a couple of the homework problems work on as well. So if we think about the simplest balance, steady state balance that we might have in a boundary layer, we could have the Coriolis force, maybe a pressure gradient, and then also a frictional force. And at the very surface, that frictional force, or actually even below the surface, the frictional force would be the divergence of a stress. So this might be the wind stress at the surface, and then down below the surface it would be turbulence stresses. And if they are diverging, then that would be what the frictional force would do. This frictional or turbulent force would impact the other part of the geostrophic balance. So without the friction, we have just geostrophic balance. With friction, we have a deviation from geostrophic balance. And so you might think about it like this: if this was for a bottom boundary layer, that there would be a finite width boundary layer attached to geostrophic flow in the interior, and as you cross that boundary layer, you would experience the stresses at the surface, and then the turbulence would carry the stresses out, diverging as they went until you got outside of the boundary layer, where the frictional or the turbulent term would be negligible. That's the basic concept of the Ekman layer. There are a few other things. So what terms are missing in this equation besides these three that we are including there? Sorry, that was a question. What other terms are missing here?
Not there because this is geostrophic.
Yeah, that's right. So the nonlinear advection and then also the time tendency term are missing. So big DDT is missing.
Yeah.
And this is the vertical derivative of the pressure. Sorry, no, that's not the vertical derivative. That's the pressure on a particular level at Z. So this is the horizontal equation we're thinking about here. There was also the vertical, the W equation, which would have the buoyancy and in it. So this could be hydrostatic, it could be non-hydrostatic. We don't know. We're not even looking at that direction of the momentum equations. So those pieces are missing, which is not an assumption about the turbulent motions necessarily, but this has kind of an implicit mean flow character to it. So if there was vertical velocities, we're kind of putting those into a turbulent character here inside this turbulent stress tensor or frictional stress tensor. And we're thinking really about the horizontal flow of a mean, which is steady in time. So the DDT term has been dropped and also steady in the horizontal, so the advection term has been dropped. So this is a simplification that's useful in boundary layers to say that things are in equilibrium. So this is an equilibrium theory. It's not changing in time, it's not changing in space, it's just thinking about balances that would happen in the forces. So we could think about it this way and think, well, if we take this term and balance the Coriolis force versus the stresses, what direction would the flow have to be in for that balance to occur? And since the Coriolis force is perpendicular to the flow direction, you start thinking about a force balance that looks something like this, with the flow going in a different direction than the stress, and the stress being opposed by the by the Coriolis force. I'm going to come back to this because this is actually a vertical integral of it's shown in this figure. So we're going to think about that a little bit more. So you can write the Ekman layer equation this way instead of this way, where we combine the pressure term, rewrite it as a geostrophic velocity, put it together. So now we're thinking about the deviation from the geostrophic velocity in the interior across that boundary layer. That's what the left-hand side. So that's the Coriolis force only on the deviation. And that should be balanced by the divergence of the stress. Or we could write it this way, just F times the ageostrophic velocity goes with the divergence of the stress. So that's a nice way of thinking about it. The ageostrophic velocity in this boundary layer in equilibrium is just there because of the divergence of the stress. So you could integrate this in the vertical, this equation, and now you start to see that the ageostrophic depth integrated ageostrophic velocity is balanced by the stress, but u here and y there. So it's the perpendicular stress at the surface that gives us the flow. So that's what this diagram is showing us. So here capital U is the depth integrated velocity. And so this force balance is not layer by layer throughout here. It's just in the integral across this boundary layer, what do the forces balance? So the surface stress is balanced by the depth integrated Coriolis force, which means that the depth integrated flow is perpendicular to the surface stress. So if you want to put this back into the iceberg context, it means that the icebergs would drift to the right of the wind. Now it's not quite as simple because there is actually a complicated spiraling pattern if we were to think not of the depth integrated part of this, but the flow just as we go depth by depth by depth across this boundary layer. We can solve that problem if we took a constant eddy viscosity, which is what Ekman did. And in fact, with that eddy viscosity in place, you can make the Ekman number, which essentially measures how important the friction term is versus the geostrophic term, the Coriolis force, the ratio of this term to this term. That's the Ekman number. Of course, the Ekman number is going to be 1 across, order 1 across this boundary layer. The frictional term needs to be as important as the Coriolis term in order to have this balance between like these terms like this. So you can also make an Ekman layer depth, which just says, suppose we set the Ekman number to 1, and that tells you that it goes like this, where it's this eddy viscosity over the friction term to the 1/2 power. In some ways, this is misleading because the eddy viscosity is not a very good parameterization. So we'll talk about ways to do this with a more realistic turbulent Ekman number later, but for now, this is kind of a nice starting point. One of the interesting and important things for those who've taken the oceanography class is that if the wind stress varies from place to place, or you have the planetary effect, which makes F vary from place to place, this Ekman layer will actually converge and diverge underneath that variable wind stress. And so you get vertical pumping at the base of the Ekman layer of injection of fluid in and out. And similarly, like this, if you had a surface rather than a solid surface, you could have Ekman pumping in and out above into the free atmosphere if you wanted to think of this as an atmospheric side. Okay, so that's the basics of the Ekman layer. Are there any questions about that before we move on? Okay, so there are a couple of Ekman layer problems in the homework that'll ask you to kind of explore these equations as we go. That's a good starting point. We're going to see a lot more kind of thinking of boundary layer physics where we're doing the same kind of thing. Thinking about maybe a DDZ term of something or other together with some kind of interior flow matching condition like this. So this is a nice mathematical starting point for what we're going to see. Okay, so now let's pick up with what Thorpe talks about. He first reminds us about Reynolds Experiment, which I hope that all of you saw in your basic fluids class, something like this. Reynolds, back in the 19th century, did this experiment where he forced flow to go through a long pipe like this, and he put dye in the flow, and at low speeds, the dye just stayed in a straight line in laminar flow, but at higher speeds, it broke up and became a kind of blurry patch. And if he took a snapshot of what the flow looked like, it actually had these kind of curling turbulent eddies embedded inside of it. So Reynolds did the dimensional analysis of this problem and actually figured that there should be a dimensionless ratio, which is now called the Reynolds number in honor of this experiment, which is the velocity of the flow, the width of this pipe, or the diameter of the pipe, divided by the viscosity of the fluid. He experimented with a couple of different fluids. He experimented with pipes of different diameter. He experimented with different flow speeds and showed that there was a critical Reynolds number beyond which turbulence developed, which is about 10,000. And so was the starting idea, was that much as we learned from instability theory, once you get a flow that's strong enough, you might get a growing instability. And since viscosity is what's damping those growing instabilities, there should be some kind of balance between the viscous forces and the advective forces. And so this ratio is really the scale of the advection term versus the scale of the viscous term, is another way to think about the Reynolds number measures in the equations of motion. Importantly for us, this is only one of the many dimensionless parameters that describes geophysical flow, because we've also got buoyancy effects, we've got stratification effects, we've got surface forcing. So we're going to think about more things other than just the Reynolds number when we think about quantifying a turbulent boundary layer in the geophysical setting. Another important experiment that was done in the 19th century was Jules' experiment. So Jules built this apparatus. Apparently he was the heir to a brewery fortune, and so he took a lot of things that he had at the brewery and built this kind of contraption out of it. The interesting part of it is this is kind of a little bit thermodynamics, this experiment, and a little bit turbulence mechanics. So the way that it works is that you can place masses on pulleys that would spin a set of propellers inside, or paddles, inside a container which could have water or some other, he also used mercury, some other liquid. And the question here was, as you exert force, as you exert work on a fluid through this mechanical system, what happens to the temperature of that fluid? And what Jules was able to show was that the change in internal energy of the fluid was, or as we know, since we've already talked about thermodynamics, that is, the change in temperature is proportional to the change in internal energy. And so the work is heat aspect of this transformation was shown by this experiment. Basically, the heavier the weight, the more the water warmed up. The lighter the weight, the less the water warmed up, and there seems to be a proportionality between the amount of work exerted as you drop a weight a certain distance. So the weight, the mass of the weight times the force of gravity times the distance dropped is the work done on this spindle, and then through the paddles, that work is making turbulence inside, and that turbulence then is heating up the fluid. And so this is one way of thinking about it. So this is not exactly the setting that we're going to think about too much, because this is a conversion from mechanical energy to internal energy. So how does this compare to our discussion of energy in the Boussinesq equations in Vallis? Any guesses? What doesn't occur in the Boussinesq equations that does occur in the Navier-Stokes equations?
Density changes in horizontal.
Yeah, density changes, and in fact, if you look carefully, remember when we derived the energy equation for the Navier-Stokes equation and the energy equation for the Boussinesq equation, and the internal energy wasn't allowed to convert. It doesn't participate in the Boussinesq equations in conversions between internal energy and mechanical energy. In order to have that conversion, you needed compressibility. So, interestingly, Jules' experiment is not the energy transfer mechanism that's relevant for the Boussinesq approximation fluid. We will find that the potential energy versus kinetic energy balance is more important in the Boussinesq setting because the internal energy, that is the heating due to the frictional dissipation, is actually not a very large effect. That kind of internal heating requires expansion and compression in a way that the Boussinesq equations show us is not very important. So it's important to think about there being energy in the temperature. It's important for us to think about that, but we'll have to think a little more sophisticated way when we have a stratified fluid about potential energy and mechanical energy, not only internal energy and mechanical energy. I hope that makes sense to everybody. Okay. So the other thing we might think about is breaking waves. And when we're thinking about the ocean surface, waves tend to break when they get steep. And this is kind of a guideline for that. So if the wave gets to be about, the height of the wave is about 1/7 of the wavelength of the wave, then they tend to break. They can be steepened by a variety of mechanisms. One thing that can steepen them is wind blowing on them. So that's what whitecaps are. That's away from shore. But another thing that can happen is that waves steepen as they approach the shoreline. Because if the amount of energy and momentum flux is conserved, as waves get into shallower water, their wavelength tends to decrease, which is a consequence of the shallow water equation waves that we already talked about. If the wavelength decreases, it means that steepness is increasing, but in addition, in order to conserve energy, their height also goes up. So the reason why I want to point this out is because when we sit at the beach and look at waves and think about turbulence in the ocean, that turbulence and breaking waves that we see there is really a near-shore phenomenon. If you look deeper out, you don't see as much wave breaking. And so the surf zone that is an important part of near-shore turbulence doesn't really have a deep water analog. So the waves are going to play a different role in deep water than they play in shallow water. You can think a little bit about wave steepening in shallow water by thinking about the wave speed that we already talked about, the square root of g times h. Well, if h has a perturbation due to the wave itself, then the crests of the wave will propagate more quickly than the troughs, and the crests will overtake the troughs, and then that'll lead to a breaker. This is sort of a hand-waving explanation of how waves break, but it's not totally wrong anyway. So that's one thing to think about. In deep water, we have to start thinking a lot about where the waves come from in the first place. And most of them that you see are actually generated from wind blowing on the surface. So we already talked about the Kelvin-Helmholtz instability. In fact, this is a particular flavor of stratified Kelvin-Helmholtz instability, where the wind is moving faster than the water below, and you get an instability, a gravity wave instability on the surface in between. This is a very similar flavor of instability that makes waves occur underneath the forcing of a wind stress. we'll talk more about how the momentum from the wind makes its way into the water, but it kind of makes its way through the waves on the way down. So if you go to the beach, which unfortunately we're probably not doing right now, we're all sitting at home. But somewhere nice like Hawaii, you can go to the beach and the breaking waves will be in this surf zone that's sort of near shore, because the waves are, as they're approaching shore, when they get into shallower water, they start steepening. So you can see the surf zone is isolated into the shallow water near the beaches, but here deeper, the waves are not as steep. But the occasional, you can see the occasional white cap either when you come into a region with shallow water, like a reef or something underneath, or maybe you can see some white caps that have to do with the winds, which here, well, you can see the winds blowing in the trees. So the surf zone is really different from the offshore breaking, is the point I want to make here. So there's lots and lots of turbulence in the surf zone that's obviously driven by converting the wave energy into turbulent energy. There's different processes farther out. Another thing that Thorpe wants us to think about is how you get relatively laminar flow that leads to small scale motions where turbulence might form. And so he took this kind of classic example of a weather system. So there's a low pressure here, and then there's a flow going, cyclonically around the low. And imagine if you put dye on the grid in this set of locations. So eventually, at first, it would look like this. And then as that dye patch advected around this low, it would get distorted. And if you actually do this quantitatively, you see that this shape, this evolving shape is what you see. So something that's initially the same width as it is height becomes something that's very, very long and very, very skinny. So this is showing us from a 2D advection diffusion equation solution what we already know about 2D turbulence, is that the energy here is going to larger scales as this long scale is tending to dominate the energy, but the entropy, the shear, is dominated by the cross feature scale, and also the tracer here has both one direction that's very sharp, has really sharp gradients, and one direction that has weaker gradients. So the stirring that distorts this feature, together with the diffusivity, leads to irreversible mixing, is the concept of this. So if we are thinking of the Reynolds number like this, this steady laminar flow is driving a velocity on an increasingly small scale. And so we can think of that as possibly leading to turbulence in the fine scale direction. Or there's another dimensionless ratio called the Peclet number, which is the velocity times the length scale divided by the diffusivity. So in this case, thinking of a tracer, the Peclet number would be getting very large, would be very large in one direction, very small in the other direction, and a small Peclet number would lead to lots of diffusion of the tracer. So this is kind of a useful way to think about how the stirring effect, the straining effect of the flow, together with diffusion, leads to irreversible mixing. So the stirring will tend to increase the gradients, at least in one direction. The diffusion will tend to decrease the gradients and will be concentrated most in the sharpest gradient direction, and so that's what mixing comes from. Does that make sense to everyone? So we've been jumping back and forth between diffusion and turbulence. So I wanted to just contrast the two concepts. So what we mean by diffusion is something that has a molecular, or it could be an eddy parameterization, an eddy diffusivity, or eddy viscosity, or molecular viscosity. And that would be something like this, where we're thinking of kind of like an Ekman layer or a boundary layer, where the big gradients in temperature are all in the vertical direction. So you might have a flux, a diffusive flux that goes like this, where the flux is flowing down the gradient, so in the opposite direction, so taking warm stuff, warm temperatures, and pushing them towards cold temperatures with some coefficient that tells you the rate at which that's occurring. Bigger gradients would lead to more diffusive flux. Smaller gradients would lead to less diffusive flux. Bigger diffusivities would lead to faster or slower, as this makes sense. The turbulent transport or turbulent flux of the same temperature quantity, we could write something like this. This is what we think of when we were talking about doing the nonlinear, when we did the Reynolds decomposition that we talked about last week, or the week, last week of class. We thought about a perturbation from the mean in the velocity and a perturbation from the mean and another thing like velocity, and we're looking at the covariance of those perturbations on average. An eddy diffusivity is finding the kappa that makes this equal to this. So these are two different things, but sometimes we'll use them interchangeably, imagining a diffusivity to be an eddy diffusivity. We could have also done this in heat flux, and since we talked about Jules Experiment already, the only thing we need to do to convert from a temperature flux to a heat flux is to multiply by the background Boussinesq density and the specific heat capacity. So this is the heat flux that goes together with the temperature transport, and this is the same thing for the turbulent heat flux. Finally, the momentum is, you could call this a momentum flux if you wanted, a viscous flux of momentum, but stress is the word that we use for a momentum flux. So a stress means momentum flux. Here's a viscous stress. Here's a turbulent stress. It is a little more, because velocity has a direction, or momentum has a direction, and also the direction of transfer has a direction. This is a more complicated system because we have to think of, this is actually a second rank tensor, because there's the direction in which the velocity or momentum is being transported, and there's the direction of the velocity momentum that is being transported. So part of it is doing the transporting, part of it is being transported, which is maybe easiest to think about when we think of it in like this in the turbulent stress. So here we're imagining a vertical transport of the horizontal velocity. So, oops, sorry, there should not be a CP there. That doesn't make any sense. That should have, that's a typo. So does that make sense to everybody? So I could have done V prime U prime, or U prime U prime, or U prime V prime, and all those different components would all be Reynolds stresses, that is the turbulent transport of momentum in different directions. Another important concept about turbulence that Thorpe wants us to think about is entrainment. So here is a plume coming out of the cooling tower. So this is hot steam coming out of the cooling tower at a power plant. And at the beginning, you can see that it's a pretty narrow plume, but as it gets higher, it's getting wider, and then it starts spreading out this way. So entrainment is the idea that a turbulent flow doesn't maintain its volume because it's entraining. That is, it's grabbing ambient fluid, so in this case, ambient air, to the sides of the plume and blending it together as it goes. So if you were to calculate the mass flux of stuff in this plume, even though mass can't be created, the mass that is behaving in a turbulent manner is getting larger and larger because it's entraining non-turbulent fluid from the environment into the turbulent plume. So Similarly, we talk about entrainment of a boundary layer, an Ekman layer, when it deepens, if say the wind picks up, will take fluid which isn't in the Ekman layer and incorporate it into the Ekman layer through entrainment. So that's an important concept to think about as well. We will get into more details of shear and strain as we go, but this is a nice little piece of just thinking about what we mean by shear. We mean when you take, when you deform a fluid perpendicular to its direction of motion is a shear, and that would tend to deform a patch of fluid like this ABCD square into a parallelogram like this ABCD later. But there are also other flow patterns which aren't necessarily shearing, and in fact in this case aren't even converging or diverging or having vorticity. This is a peculiar flow field where the you get a what's called a confluence or a diffluence. That is, the streamlines are moving apart or the streamlines are moving together in different parts of the flow, which deforms this initial patch of fluid, but it manages to do it without divergence or vorticity. So this is an interesting class of flow that we'll think about when we think about 2D flows. Let me see what we're almost out of time, so why don't I switch and let's ask questions and pause here, because I think the next pieces are kind of a change of pace to start thinking about stratification. Are there any questions about this stuff?
Sorry, so the above figure is shearing and the below figure is straining. Is that?
Yes. So technically what we would say is the lower figure has a strain rate even though it doesn't have divergence or vorticity, which is kind of a peculiar case. But the rate of strain tensor, which is the gradient of the velocity, so the x derivative of u, the y derivative of u, the z derivative of u, the x derivative of v, the y derivative of v, the z derivative of v, that's the velocity gradient tensor, which has both a strain and a rotating component to it. So this is just an example of a strain flow. Shear and strain are not describing quite the same thing. Shear is talking about a velocity gradient in a direction perpendicular to the direction of that velocity, if that makes sense. We're going to get more into detail about how to think about the velocity gradients and the velocity gradient tensor and the strain rate and the shear and the vorticity. Think about that again. It's kind of different. It's different linear algebra operations on the velocity gradient tensor. Are there other questions? So does everybody understand a little bit more about the Ekman layer now and feel comfortable with doing the homework on the Ekman layer? Okay, and how do people feel about the way that this format worked? Any suggestions for improvement? Okay, and so I'm going to save the video and upload that to YouTube like we normally do and put the link. So we'll also have a video version if you've forgotten something you want to revisit. I've also put a PDF of the slides, so it doesn't have the movies, but it has the slides. Is also linked. I'm going to add more slides to talk about stuff for Wednesday, so you can't quite look at that in advance, but you can read through Thorpe. So we're going to finish up chapter 1 and then move into chapter 2 of Thorpe next week, which is going to talk about how we measure the boundary layer. And then, actually, we'll probably do a little bit of chapter 3 as well on Wednesday. and then we'll go, and then so that will put you. You'll be totally ready to do the homework, which we can discuss questions from the homework on Friday as we normally do, and I'll have the homework key provided for everybody on Friday as well. Does that make sense? And then next week we're gonna transition over to WinGuard for a couple of discussions about the atmospheric boundary layer. And I haven't decided which chapters and which sections are the right thing. I'm gonna try and be precise about not over duplicating. And then the next homework won't be due for 2 weeks, so we'll have a chance to get some more steam together on some of the more quantitative aspects of turbulence before that next homework. And obviously, as always, feel free to email me, feel free to contact me or ask in the chat box here. It would have been a good way to ask questions. I think it would be helpful if people were actually using the chat box and having a discussion among each other, because it is obviously awkward to interrupt and like disrupt the flow of the conversation. But I find it really helpful when the chat box, to use the chat box at the side to ask questions of other people who are not the speaker at the same time for clarification. So please do that. I'll try and keep an eye on the chat box, but I think that would actually be a really helpful thing for as we figure out how to use this format better. Okay, cool. Thanks everybody. I will see you on Wednesday.
Thank you.
Mm-hmm.